The major protective device on the steam turbine is the main steam stop valve. If it becomes necessary to stop the turbine due to an abnormal operating condition, the stop valve must be tripped closed. In the case of a reheat turbine, both the main steam stop valve and the reheat stop valve will be tripped simultaneously. We have already learned that the stop valve is closed by actuation of the pilot relay or trip relay, which drains oil pressure from the hydraulic system. There may be several trip relays located on the hydraulic system, actuated by different protection devices. Operation of any trip relay should cause the following action: closure of main steam stop valve, closure of reheat stop valve, closure of steam admission valves, positive closure of extraction line non-return valves, trip open the generator breaker, trip open the generator field circuit breaker, and activation of alarms and annunciation. So what are these hazardous conditions that are considered severe enough to automatically trip the turbine? Well, the most dangerous condition that must be avoided is that of overspeed. And this could occur in the case of a load rejection, for example. Similarly, we would get the same result if the generator breaker was tripped open by mistake when the unit was loaded to about 50% capacity. Of course, the turbine generator would immediately increase speed because at the instant of the breaker trip, a very large quantity of steam is flowing through the turbine. Under normal circumstances, the governor should be able to close the turbine control valve sufficiently to bring the speed close to normal within a few seconds. However, imagine what would happen if the governor failed to act properly, or the power piston seized, or some other defect prevented movement of the control valves. In this case, steam flow to the turbine would continue, with the result that the speed would rapidly rise to 2 or 3 times normal. In practice, the speed would not get that far, because centrifugal force acting on the mechanical turbine and generator rotor would cause them to break up. Several instances have been reported of turbine blades and sectors of turbine wheels passing right through the turbine shell into the turbine room, with the potential for injury to plant staff and damage to other equipment. In order to prevent this possibility, 1 and sometimes 2 quite separate overspeed protection devices are installed and set to operate at 10% and 12% overspeed. Each protection device operates a trip relay to close the stop valve and other protective action, as already discussed. Here we see an example of a traditional mechanical overspeed device. Essentially, it consists of a bolt inserted into the shaft. As the shaft rotates, the bolt tries to fly out by centrifugal force, but this is restrained by a compression spring. The spring is carefully adjusted so that the centrifugal force does overcome the spring compression at 10% overspeed. The bolt then mechanically trips the latch, which allows the trip relay to move to the trip position, so draining off hydraulic oil and closing the stop valve. You will remember that tripping the stop valve also actuates the positive closure of non-return valves on the extraction lines. This is necessary to prevent entrained steam being drawn back into the turbine and aggravating the overspeed condition. Another common type of overspeed relay uses electrical measurement of speed and an electrical circuit to initiate operation of the trip relay through a solenoid. It is vital that these overspeed trips be checked for operation at regular intervals and the actual tripping speed be recorded. Now, this may be done when the unit is shut down or started up. Adjustment of the setting may have to be made from time to time. This protection device is one of the most important on the turbine. On a condensing turbine, we expect pressure in the condenser and therefore at the turbine exhaust to be between 1 to 3 inches of mercury, depending upon the actual cooling water system. Now imagine what would happen if the back pressure started to rise, perhaps due to a large air into the condenser, or more likely a reduction in cooling water flow through the condenser. Now remember, as the back pressure increases, so does the density of steam at the turbine exhaust. With a back pressure of 10 inches, the density would be about 9 times greater than the density at 1 inch back pressure. This increase in density greatly increases the friction on the LP blading, which is still turning at 3,600 RPM. The result leads to overheating and possible damage to the low-pressure blading. In order to prevent this situation, a vacuum continuously monitors the back pressure, and it is usually set to operate a trip relay when the back pressure reaches 10 inches of mercury. The monitor will sound an alarm when the back pressure reaches 5 inches mercury, so as to warn the operator to take action before a trip occurs. While we're talking about back pressure at the turbine exhaust, let's consider what would happen if during a startup we passed steam through the turbine before establishing cooling water flow through the condenser. Well, the steam entering the condenser would not condense and consequently would build up pressure eventually to such a level as to rupture the exhaust hood. In order to prevent such an occurrence, a large relief diaphragm is fitted to the exhaust hood. This is normally held in place simply by the vacuum inside the hood and atmospheric air pressure outside. As soon as the pressure inside the hood rises above atmospheric, the diaphragm opens, acting as a relief valve to prevent any damage to the exhaust hood casing. This diaphragm works quite independently of the mechanical devices and hydraulic mechanism that we have been discussing. Usually the only attention required is to make sure that the water seal around the edge of the diaphragm is not leaking and allowing air to enter the condenser. Another important protection device that is set to trip is the thrust-bearing failure monitor. This equipment is fitted to precisely measure the position of the thrust collar in relation to its pedestal. As long as the thrust bearing on either side of the collar is operating correctly, there will be no change in the relative position of the collar, even when the turbine shell and the turbine rotor expand. If the thrust bearing were to fail, allowing axial movement of the rotor, we could run into the serious problem of contact between the rotating and stationary blades. Therefore, it is essential that at the first sign of thrust collar moving failure of the thrust bearing, the trip relay be activated so as to close the stop valve and bring the turbine to a halt. Another condition which will cause the turbine stop valve to trip is loss of lube oil pressure. If lube oil is not available to provide lubrication to an operating machine, the bearings will rapidly overheat and fail, with possible disastrous consequences for other components of the turbine and generator. Lube oil is monitored continuously, and if pressure falls zero or a very low value, a trip relay will be actuated to trip the turbine. Note that this relay will also prevent the opening of the turbine stop valve if lube oil circulation has not already been established during startup. In the case of hydraulic oil, an alarm is usually fitted to indicate low pressure. But a trip relay is not always provided. This is because the hydraulic equipment is designed to operate in a fail-safe manner. If the hydraulic oil pressure fails, both the stop valve and control valve will be closed by spring pressure in their respective power cylinders. In addition to the protective devices mentioned, the operator has the option to trip the unit manually by trip lever, which is usually located on the turbine pedestal. On most units, it is necessary for the operator to reset the trip mechanism manually at the turbine pedestal after any trip has occurred. The operator can only unit remotely from the control room. This is simply a remotely operated solenoid which operates the. This solenoid trip may also be activated by certain generator and boiler protection. For example, if an internal fault developed inside the generator generator, it would be necessary to trip the generator breaker and the field also the turbine stop valve to bring the generator to a stop as soon as possible. Similarly, if a fault on the boiler was serious enough to cause a boiler trip, then the turbine stop valve would also need to be tripped at the same time. Otherwise, we would be pulling steam and possibly water out of a shutdown boiler. Summarizing then, let's list the major that are installed on most steam turbines: main and reheat stop valves and associated hydraulic trip relays, positive closing non-return valves on extraction steam lines, overspeed trip, low vacuum trip, thrust bearing failure trip, loss of lube oil pressure trip, manual trip lever on the front pedestal, remote solenoid trip by operator push button, and generator or boiler protection intertripping. It is vital that all protection devices be tested regularly to ensure that they will actually operate when required. In some plants, the turbine generator may remain on load for many time. In this case, some form of simulated test may be carried out. For example, partial operation of the overspeed trip is actuated, but actual tripping of the turbine is blocked. An extremely important test maneuver is the exercising of the turbine stop valves. The test circuit allows the stop valve to partially close and then open again. This test is performed daily in many plants, and the objective is to make sure that the stop valve does actually move and not remain frozen in the open position, as has actually occurred on some occasions. All of the protection devices in the no use whatsoever if the stop valve failed to close when commanded. For a similar reason, the positive closing non-return valves on the extraction lines are also exercised daily or at some other regular interval. Make sure that you are thoroughly familiar with the established procedures for testing protective equipment on your turbines. Also, using the information that we have presented here, make sure that you know the function and location of all protective devices on your particular turbines. And note that there are certain items of equipment that could be considered protective, but they do not actuate the stop valve and shut down the turbine. Pressure deloading device is often connected to the hydraulic control valve system. The objective of the deloader is to protect the turbine against falling steam pressure from the boiler. For example, a defect on the boiler auxiliary plant may reduce steam output from the boiler. But as the turbine is not aware of this, it will continue to pull the same steam flow out of the boiler, with the consequence that the pressure falls and will continue to fall as long as this condition prevails. The danger is that with falling pressure, the water level in the boiler drum will rise substantially due to swell, and this in turn may lead to carryover, that is, water passing along with the steam into the turbine. To prevent this possibility, the deloading device monitors the steam pressure. If this falls below 80% of nominal, the deloader starts to close the control valves to maintain the steam pressure at 80%. Of course, this will reduce the output of the turbine generator, but this is far preferable to damaging the turbine. During startup of the unit, which may well take place at low steam pressure, the deloading device is bypassed and only brought into service when the unit is on load and boiler pressure is normal. Most of the turbine operations are performed remotely from the central control room. Regular local inspection by a roving operator. In traditional control rooms, the operator works at a large switching controls, indicating lights, indicating instruments, and recording charts for that is, boiler, turbine, generator, and auxiliaries. The annunciator panel, usually located above, provides indication of any alarm conditions. Newer plant installations, and in fact in many converted plants, control systems are employed, and in this case the operator works at a console with three or four CRTs, providing indications, alarms, and the means for remote operation. Referring to turbine operation, the indications we are most interested in are steam conditions, that is, pressure and temperature, vacuum, usually dependent upon certain water conditions, lube oil temperatures, bearing vibration, and mechanical condition of the turbine as indicated by the supervisory instruments. Now, in this module, we have only been able to cover the most common features of turbine operation. Using this information as a guide, you must make sure to thoroughly learn and become familiar with your own turbine. No doubt each of your machines will have their own idiosyncrasies, which become well known to the experienced operator. Please switch off the